My name is Shvank Misra, and this is my video lab report for Intro Physics 2212 at Georgia Tech. This lab is based on the charged tapes experiment. I'll first introduce some key ideas, relevant formulae, and go over my setup and experimental data. I'll then show you around my computational model, whose link is in the description to this video, and take a look at my program's output. We'll then take a look at some of the results and some simplifications we've made to arrive at these results. And finally, we'll answer some key questions about the lab. So the key ideas in this lab are Coulomb's law, which basically describes the electric force between two charged particles a certain distance apart with a certain charge each. Electric field is the force created by a charged particle. The electric field can be thought of as the force a small positive test charge would feel at a certain location due to a charged particle, and hence the units for electric field are newtons per coulomb. The force due to gravity is an attractive force, and for this lab is simplified for use near the Earth's surface. And the last key idea is just knowing how to use and manipulate vectors, which are just a magnitude and a direction. So here are the formulae for Coulomb's law, an electric field due to a point charge, the relationship between force and electric field, and the force due to gravity close to Earth's surface. I'm not going to go over all of these formulas as they're fairly self-explanatory, but you may take a look over them if you so wish. So here's a diagram of the setup, where we floated tape B by holding tape A below it. The separation distance between tape A and tape B, as well as the mass, length, and width of tape B are all shown to the right. So here's a look at my computational model, and as you can see, I've defined a function to calculate the force between two charged particles as per Coulomb's law. I calculate Q1, Q2, R mag, and R hat, and then apply the formula. For this lab specifically, I also went ahead and set the force due to gravity equal to the negative of the electric force, as they balance each other out, as seen in the free body diagram to the right. I then print out the relevant output, which we'll see in just a second. And lastly, I also define a very simple function to calculate electric field using the formula from before. So here's the output of my program. The orange arrows are the electric force on each particle, tape A and tape B, due to the other tape. Tape B is at the top, and since it is the one we're interested in for this lab, I've also included the force due to gravity in green. And you can also see the numerical output of the program to the right, which we will compare to the mathematical calculations in the next slide. So as you can see, the magnitude of charge as per the computational model is 1.857 times 10 to the negative 9 coulombs. And as you can see below, doing the calculations by hand yields the same result. I found my tape to be negatively charged as it was repelled by a negatively charged pen which was rubbed against my clothes. Here are a few other results. I also found the number of atoms in tape B to be roughly 3.564 times 10 to the 17, and the number of electrons to be roughly 1.161 times 10 to the 10. One assumption I made when calculating the number of atoms was that the tape was a sheet that was only one atom thick, which may not actually be the case. As for these assumptions, the first one does not apply, as tape B is static once it floats, so air resistance on a moving object is irrelevant to this lab. The second assumption does apply, as this is exactly what we did for both tape A and tape B to calculate the force between them and the electric field due to tape A on tape B. The third assumption also applies, as we did assume that the charges on the two tapes were the same. We could reasonably assume this since the two tapes were charged in exactly the same manner. As for this discussion question, what would happen if electrons had positive charge and protons had negative charge? Simply put, this would have no effect on our observations, as this scenario playing out would be akin to a change in physics convention without any real impact on the world and our observations. And lastly, why do we take great care when handling charged tapes? Well, this has to do with the fact that any time a charged tape comes into contact with a surface, if there are any excess electrons, they tend to escape, and if there is a deficiency of electrons, the new electrons from the surface tend to flow into the tape. Both of these situations would cause the tape to lose its charge. Thus, we handle them as little as possible so that they retain as much charge as possible so that we can carry out our experiment properly. Thank you for your time and have a nice day.